So this is the definition. So here are two examples. So let's look at the left one. Is this a tree? Why? Because it is obviously connected graph because A, B, and C are connected. Where I assume here transitivity. So generally, if there is connection between A and B, and B and C, I'm assuming that A and C are also connected, and then the same way C and D, C and E, and C and F. So there are no circuits. So basically, there are unique paths from every vertex. Sometimes we call them nodes as well. So from every vertex, there's a unique path to another one, and as I said, there are no circuits. So what about this graph here? No, this one is not a tree because you have alternative. You have a circuit, and then even if it is connected. So here it is that a proposition says a graph is a tree if for every two vertices there exists unique path connecting them. So can someone argue why would this be true? It's a simple proof. So what? If so proposition. One. So a graph is a tree for every two vertices. There exists a unique path connecting them. Let's practice proofs again and reasoning. So if a graph is a tree, we need to show that there is, so for every two vertices, so let G be a graph, be a tree. And let U and V be its vertices. Then what? Is there a path connecting them, yes or no? Why? Tree meaning what? Because it's connected. So it is connected, so there exists a path connecting them. Definition says if there is a walk connecting them, but we proved last time that that walk could be trimmed to get a path. So there exists a path connecting them. Why is it unique? Because if we had two of them, then we would be able. So if this is U, this is V, this is just, instead of writing two sentences, I'll just draw a picture. If there is one path from U to V, and there is another path from U to V, what can you do? Go from U to V and reverse the second one and get what? Circuit, which is contradicting. So I used here argument by contradiction. What about the other way around? If there exists a unique path connecting them, what? Then again, it is connected if there exists a unique path. Then what? Then it is connected because there exists path. And what else? Why there is no circuit? There is no circuit because why? Because if you have a circuit, then what can you do? Pick any two vertices, and then between them you can go clockwise and counterclockwise and get two different paths again. So generally, this is really saying the same thing in two different languages. In two different sentences, it's obviously that this theorem is true. Let me give you one of the nicest examples of trees that are very important and are being neglected to lots of harm to mathematics. What is it? And you know, when people study mathematics, one of the biggest problems for young students of mathematics is order of operation. That's where you really lose your first 30% of population. Like, they never go beyond that. It's just, it's complicated. So what? So generally, if you say something like this, A plus B, yes, A plus B, let me see if I know this. A plus B squared times 3, and then plus, or times 3 plus 7, let's say something like this, okay? Then 7 divided by 4, something like that. So what? Then when you read, what is the problem here? That this mathematical expression is generally read from left to right. Why? We have a habit to read things from left to right. Do you agree? But actually, math expressions are not executed from left to right. They are executed according to priorities. Do you agree? So what do these priorities say? Then they say those PEMDAS, parentheses first, and then what? Exponents, and so on and so on. And it takes forever. And what? The moment they lose concentration, they start messing it up and do whatever it's easier for them. Generally, where is here a tree, actually? Each mathematical expression is built according to a tree structure. So instead of writing this, we should write the following. Take all your inputs, A and B. 3, 7, and 4. And instead of writing the way we write, unfortunately, we should write things like this. Here is your plus. And then what else? What do I do with that plus? Square it. So here's the square operation. That is unary operation. Then what do? Whatever you obtain there and 3, you just multiply them. Do you agree? What else do we do?
7
and we divide 7 and 4, and at the end, what do? We add them up. And that's, so if we were writing math expressions this way, would people ever have any troubles doing this calculation? No, because can they start it from here and first calculate 7 and 4, yes or no? Yeah. Yes, as long as priorities are designed according to the tree. So generally, of course, if they don't miss anything, they can calculate this guy here, and of course this guy will wait until its left node is being calculated. Do you agree? And then what? This one needs to wait until those two. So generally what? You just fill in this and go down the tree. You calculate A plus B. When you are done, you square it. There's no other way. Now when you have those, you say, who's my right one for multiplication? You pick it up. If it's missing, you then calculate. What else? Another thing that you kind of had to do in pre-calculus. What if I have this? But generally, what if I have this? 3x squared plus 7 over 4. Let's say someone understands this, but they have troubles with this. What's 3x squared plus 7 for? Can I make a quickly 3 for that one? What is that? You take an x. What do you do with it? Square it. What do you do then? Times 3. So take a 3 and square and multiply. Take 7, take 4, divide, and then what do you do? Bad. So my question is, what happened here from this one? I did so-called substitution. Instead of x, I wrote what? A plus b. You know what substitution basically? You even see it better on a tree. Here it is. So A plus B looks like this. A, B, A plus B. Do you agree? And that's why we often say cut and paste. Cut this X and paste the whole tree and get for it. Here's your substitution. Now you will get this one. So generally, when you replace expression into expression, what you are doing, you are taking a node and then you are making a whole tree out of it. And that tree is actually what you are replacing inside. So generally, two quite kind of distracting math operations are really very nicely visualized using trees. And by the way, what? Is this a tree, yes or no? Yes, actually, and that's why trees are so important for all kinds of applications, because each member has only one history. So to get to this, you'll see toward the end of the class, although we'll draw them from tree down, generally, wherever you are, from each leaf, so-called, or terminal vertex, there's only one way to go all the way to the bottom of the story. Do you agree? So that's that uniqueness of the path. So generally, if you have an address, from that address you can exactly recover how did we come to that address. And that's why trees are so important to store data and to search, to organize them for databases and to store data, to search for them, and so on and so on. So that uniqueness of paths through the tree is essential for many applications. Yes?
Is there a name for, like, because this looks like an upside-down version of the tree? Different name, or is it all just
no, people just draw it however they like it. Yes. So generally, in the notes, I always did it upside down. So not tree going up, but going down. But this is my old habit from expressions to draw them up. So it's just a visual connection are the same. For example, what? This node here is called the root. So it's a little strange if you call it a root if it starts from it. But again, if you think of it as a root kind of building the mass toward the others, then that's splitting the mass toward the feces, like in probability, then that actually makes more sense to draw it the other way around. So it's up to you how you want to draw it. All right, what is the other example of a tree? For example, decision making. So decision making is very often a tree. So what? You say the following. So what? For example, you are making a schedule, and then you say the following. So what? You are looking which math course you're going to sign up for spring semester, and then you say what? All right, if I sign up for math 260, or I sign up for math 270, or you sign up for what? For math, what's the other one? 265, yes, I know there is a course like that. Yes, all right, so here it is. So for example, someone is trying to sign up for one of these three courses. And then what? If you sign up for 270, then, all right, but then if you sign up for math 270, you immediately must sign up also for what? For math 260, because they are prerequisites. So this one says, oh, I have to sign up for math 260 as my second course immediately, if I want to do that. And then what? Then, for example, on the next one you say, yes, but if I have math 260, I can sign up for physics. I don't know the structure enough, but generally, then physics 151, or you can do both option, physics 153, that's a little different. And then math 265, again, this one is compatible with with, for example, physics 200, and this is physics 210, then let's say something like this. And then what? Your schedule then is schedule of 2 courses, let's say, and then your schedule is generally path along the tree. For example, you're going to sign up for these 2 math physics courses, or you're going to sign up for those 2, but generally each of those paths gives you a consistent choice that is consistent, that registrar will not object or something like that. Yes?
I always thought that the leaf in the tree has to be unique.
What's it?
I always thought that the leaf in the tree has to be unique.
The leaf?
Yeah, the
Like
end
the
node.
terminating point?
Yeah, that terminals. What do you mean?
Because it's not unique. The 260 is twice.
It's not a terminating point twice.
Yeah, but you could still have 2 different.
No.
You could still do 2 different.
No. I mean that this and this doesn't matter, because you can say the following. This is Math 260 chosen as a second course, let's say. Math 260 as a second course. So it doesn't matter. Name of the, because this is the decision made after you signed up for Math 270, and this one is not. Yes?
So you could you have 260 coming out of 265? Or would that not work?
No, then it wouldn't be a tree. You would have a cycle then. So this is like Math 260 as a second course, because that Math 260 and this Math 260 are not the same thing. Otherwise, you would have a circuit. All right.
So they don't have to be identical in their entire route, just that they have an identical term in the same order, or in the same place. Like, could you not have another 260 as a first course?
But here it is. You have to think of this as different from this. You must have a different node. Because otherwise, if I connect it, then I don't know to which Math 260 to connect. Yes, something like that. Yes. So Math 260 as your second course, or something like that. All right. What is the other example of a tree? So we have trees quite often. We already had trees when we calculated the multiplication principle. You remember multiplication principle when we counted number of options? Or even more well-known one is when you have like heads and tails, and let's say we have 3 tossings of the coin, and then we have heads and tails, and then what happens on each on the first tossing, you can have heads or tails. And then each of them, and then the same situation as here. This head is the same. This is head on the first attempt. This is head on the second one. Heads and tails, heads and tails. And then again, you have heads and tails, heads and tails, and then heads and tails. So what now? So for example, this tree records possible results on tossing 3 coins, or the same coin 3 times. So here, each tossing on the first attempt has 2 branchings on the second attempt, and then each of them has 2 branchings on the third attempt. So generally what? Yes?
So if you did like a tree for like prime factorization, you had a 2 on each level, that would be okay?
For prime factorization, what was that?
Number, and you break it down to its most like minimal prime factors, like you just
Okay.
take 2 out of it, or 3 or 5.
Uh-huh.
Tree 2.
Let me see what you're asking me. So, yes. So then on a factor, like yes. So that's like 120. Then you break it like this. Is that what you want to say?
Yeah.
10, 12, yes. Yes, and then 2, 5, and then again you have 2, 6 as second 2, yes. So generally, and then this one factors as 2 and 3, and then yes. So here you have a 3 telling you actually how you can write your 120. So you can write your 120, actually you come to this, what I had here for the expression, because now you can write this as 2 times 5, and actually 3 tells you how to put parentheses. So the way I broke it, it could be broken in different ways. You have 2 times 5, and then for 12, you have what? 2 times 3. So this would be so this 3 actually tells you how you broke how you place the parentheses. Because otherwise, I can break it as 2 times 60, and then it would be 2 here alone, and then 60 would be broken here, and you would get the different the different placing of parentheses, although unique factorization theorem tells us that there must be the same factors on car.
So you can, in a tree, you can have nodes that have the same value, but as long as they have a unique path to get to them, they're...
Exactly. So generally, even if you see the same, even if you see the same number, you can just say 2 as a factor, left factor, or right, first appearance, second appearance, third. What else? When you do binary representation of a number, you have zeros and ones all the time. And then, of course, but those are nodes. Actually, you can think of this as the following. This h here, you're actually more encoding it as HH, H on the first and H on the second. Yes?
So when you're doing this prime factorization, though, you're doing it in the binary method, correct?
No. Generally, that's how we break a number, because you can only multiply 2 numbers at a time.
So I was just thinking if you had, okay, that's what I was saying. You're
Yes.
saying you can only do 2.
Yes, of course.
So I was thinking
If
when
you
took 16, you just went 4 2s.
yes, but you are doing the shortcut. You are actually running through the tree. But tree itself only has multiplication. It must have 2 branching because it's binary operation. Yes.
So that is a binary tree, the field tree?
Yes, exactly. That definition is coming. Generally, binary tree, and here's the terminology. Binary tree means that you cannot have more than 2 branchings. But you are allowed to have one only. So, by the way, in this case, by the way, let me fix the terminology. So, if I have this node in my tree, then all the nodes preceding or vertices preceding that, the first element is, we very often assign one element as a root of a tree. Starting element, those are called the rooted trees. So this is the root of a tree. So this is a rooted tree as well. And then what? Then from every element, from root to any element, there is a unique path. Do we know that? And along that path, we say all these elements are ancestors of that vertex. And the element directly preceding our element is called a parent node or parent vertex, and that's standard terminology. So this is parent, this is child, and then what? If in our tree no vertex is allowed to have more than 2 children, then we call that binary tree. So this one is what? Binary tree, because we never have branching more than twice.
Would basically be empty set?
Not really.
Okay.
I wouldn't think of it that way. Although, if you think in that inclusion order that we had in chapter 6, empty set would be there. So empty set, you had even on exam 3, you had someone who is actually the smallest element. So smallest element sometimes could be considered as a root. But the root sometimes is just assigned without any kind of special property. You just assign that one and then develop everything from the perspective of that element. So that's the terminology. By the way, there's also a term of full binary tree. What's full binary tree? you always branch twice. So whenever you branch twice. So for example, we just cover quite many definitions. Is this a tree? Yes. Is it binary? Is it full binary? No. What's missing? This one, it didn't branch at all. And then what about this one? It's not even binary at all. Why? Because it has triple branching here. So these are definitions, but they all have a root. Someone had hand in the air. Someone wanted to comment.
I did, but question was answered.
Okay, perfect. That's good. All right. Here is an interesting theorem. Tree has a very interesting connection between the number of vertices and number of edges. So is this a tree? Yes. Let's count how many vertices does it have. 1, 2, 3, 4, 5, 6, 7. 7 vertices. Do you agree? How many edges? 1, 2, 3, 4, 5, 6 edges. Is that always true?
Every tree has n minus 1 edge.
So number of edges is 1 less than number of vertices. Why is that?
It has to be,
Every
right?
vertex has an edge, plus there's one vertex at the end.
So generally, what? Whenever you want to introduce, think of tree as growing, then every vertex has to be introduced how? By an edge. If you want a new vertex, you just must add one edge. You cannot add more, do you agree? Because otherwise you would make a circuit. And then, so that kind of makes sense. But can we give a formal proof? How would the formal proof go?
By induction.
That's it. So proof by induction. So theorem. So by now, I hope everybody is aware how important it was to learn an induction, because here we would be just really left without a very important tool for proving theorems. And by the way, graphs are one of the most popular topics for investigation in logic also. Why? Because they have fairly simple structure, and then you can just exercise many general logical theorems among them. Because sets are the simplest structure in mathematics, and then next one are graphs, because they are just elements and connections. That's the next thing. No, nothing fancy, no functions, no continuity, no big things like calculus. All right. What's that?
What's after graphs?
Here.
What comes after graphs?
In that simplicity, probably some configurations with a little bit of geometry, like little projective geometries or something like that. So a little geometry on it is probably next. I might be wrong. This is too. Some people might disagree with that. Yeah, you must add geometry, except connections. I think so. All right. So theorem 7.4. Theorem 7.4.2. A graph with n vertices has n minus 1 edges. 3, sorry.
That was on like test 1, the propositional logic. You had like a sufficient and necessary.
Oh, did I put it there?
Yeah.
I see.
I didn't know what it meant, but I remembered it.
That's exactly what I wanted, so that you know how to manipulate things even when they do not make sense to you, because that's what logic should be able to do. Oh, I see. Nice.
So like a graph, it's a tree with n minus 1.
Yeah, so tree with n vertices has n minus 1 edges. Why is that? Proof. By induction on n.
Single vertex has no edges.
Exactly. So if you have, n equals 1, we have just one vertex. There's nobody to connect to. And Oops, I forgot something in the main definition of a graph. What else? It's a simple, we all the time work with simple graphs, but its definition should always, why did I miss that simple now? Because otherwise you would have a loop maybe, and then loop would ruin all this. So generally graph has to be simple in order to be a tree. So if n equals 1, you don't have a loop and there's nobody else to connect, so 0 edges, and that's exactly true. So assume true. Assume the statement is true for trees with n equals k vertices. Now let G be a tree with n equals k plus 1 vertices. Now I have a little trouble. I want, because what? I would like to remove one vertex and hopefully to cut off one edge, but I'm a little bit afraid that things might get disconnected. Imagine that I have a tree like this. Trees like this, and then I want to remove one vertex, but if I remove this vertex, what happens? Because, why do I want to remove it? So that I call inductive hypothesis. That's business always. You go from one level to the one that you already control. But if I remove a vertex, I might lose connectedness of the graph, and then I cannot call the theorem. What should I do? Do it carefully. That means what? It has to be what we call terminal vertex. Do I have a terminal vertex always?
Yes, you.
Why?
Because even if you have one n equals 1, that's the terminal one.
No, but why does every graph has a terminal vertex?
There's no circuit.
What's it?
There's no circuit.
Exactly. So generally what? I start from one vertex, whatever it is, and then if it's connected to something, I'll call that V2. And then what? Is this connected also to something else, yes or no? If it's not, then it's a terminal. So I can always progress, and then what? At the end, there's someone who's not connected to anything else. Why? Because the tree is what? Finite. So if it's finite, going from so if I have V0 start, then V1, next one V2. If there is someone to connect, okay, that's V3. So I make a path longer and longer. At the end, I might exhaust all the vertices or whatever it is. At the end, I will have a terminal vertex. So it's very important to to kind of identify one terminal vertex. So let V be one terminal vertex. So again, lots of terminology. When do we call a vertex terminal? If degree is how much? 1. That means someone brings you the connection and that's it. You don't pass it on to someone else. One terminal vertex, that means degree of that vertex equals to 1. I just explained, I'm not going to write it on the board, why we always must have that one. So what happens? Let us remove V. Oops, too early. Let W be the vertex connected to V via an edge E. So here is that V, that terminal, not in the middle, and then here is the edge E. So what do I do? Now it is, yes.
Could you also remove
A root?
yeah, if there's only one connection?
No, because, that's where actually I look at the both books, Epps' book and both what the name of the most famous book in discrete mathematics? Rosen, thank you. Both of them gave a fairly careless definition of a root because they didn't require for a root to have degree 2. So then by their definitions, the root could be considered to be a terminal vertex, which would be very dangerous and bad. So generally, why is that not a big deal to require? Because if you have something like this, then you start calling it a root when the branching starts, and then that stem is not interesting. So generally, I will call root only the part when the branching starts, because I don't want to start, because then you have always to make exclusions about that, because technically a root would be a terminal vertex. Or you have to say a vertex is terminal if it has degree 1 and it is not a root and all that. So it's more elegant to just require branching at the root. And then, disregard everything that comes before that, because there's nothing else, that it connects to that influences behavior. So anyway, so what happens? We identify one vertex V, which is terminal, and one edge E connected with something else. So who do we cut off?
V.
We cut off a V and the edge E. Remove V and the edge E. What happens? When we remove this, what's left? This tree, is it still connected, yes or no? Because nobody needed connections through V, because there are no connections through V, so nobody lost connectivity. And then what? We didn't build circuits, of course. Graph is still simple, so it is a tree. How many vertices does it have? No, I started with k plus 1 when you remove 1. So this T prime has what? K vertices. And what? K vertices. So, according to inductive hypothesis, it must have how many edges? K minus 1 edges. And then our graph has how many vertices? K plus 1 vertices. And how many edges? K minus 1, and that plus this one that we cut. So that's K, so everything matches. As I said, these are very simple proofs, but they are good exercise in our induction and how to organize sentences and everything. And basically what? I just did what we said immediately in one sentence. We said every vertex, new vertex, has to come through an edge, and its unique edge. So every new vertex is a new edge. But this is just formal proof by induction. Now I'll ask you the following question. Do you think that the converse is true? If you have a graph that has n vertices and n minus edges, does it have to be a tree? So if you say no, you should give me a counterexample. So let me write that on the board. So E is the converse, and then we'll take a break. So question, is the converse true? That means, which means what? If a simple graph, because if you allow multiple, of course, it's a mess. Nothing works for them. So if a simple graph has n vertices and n minus 1 edges, does it need to be a tree? That's a question. So if you say yes, I'd like to see a proof. If you say no, I'd like to see a counterexample. And if you want to make counterexample, what's always the best? As little as possible, with 2 vertices, 3 vertices. Yes?
Could you not just have a disconnected graph that has one node that's connected to itself and another node?
What are you suggest? So you are giving me counterexample to what I said. So what?
Have one node that's connected to itself?
No, it's a simple one. Simple graph.
Oh, no. But if you have, 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 if you have,
simple graph, because without simple everything is, you just,
Disconnected
what's
simple
it?
graph. You can have a disconnected simple graph.
The way I said it, that would be counterexample. So theorem, so give me a disconnected one then. So,
A and B not connected to each other.
okay, how many vertices?
Two,
How many edges?
no,
0. And then, so what?
have one C.
But, and what? It is not a tree, and that's it. So number cannot build you connectedness. So I have to improve this. What should I say?
If you add point C and then connect A, B, then you've got.
No, then it would match. It would, so here it is. This is a graph with 2 vertices. No, you didn't give me counterexample. You need to give me one edge, and you didn't give me one. So this is not a good
It's a
counterexample.
simple connected graph.
What's it?
It's a simple connected graph.
Oh, but if you
With the
add
tree.
another one, you draw one edge, then you have
The-
one edge. But if you
So what's it?
The tree assumes that it's a simple connected graph.
Okay.
So those would have to.
Yes, but here it is. But you didn't give me counterexample. You need to find me something that has n vertices and n minus 1 edges and fails connectedness and being done. Yes.
So if you draw a point C and D and then connect A, B, C, D, or A, B, C, then you've got.
Like this.
Yeah,
Oh,
then
wait
you've
a
got
minute.
three